Experience at leading international institutions, including Khalifa University, Abu Dhabi, Prince Sultan University, Saudi Arabia, and IIT Delhi. His research interests span power quality, smart grid, renewable energy integration, and power electronic converter design. He is a recipient of multiple Best Thesis and Best Paper awards from IEEE sponsored conferences. So we are delighted to have him as our resource person for this session. I welcome Dr. Nirmal Mukundan for the presentation. Welcome, sir.
Thank you, Agri sir. Thank you for the nice intro. Am I audible?
Yes, sir.
Yeah, carry on.
Yes, sir.
I hope you can see my slides, right?
Yes,
sir.
Yeah, okay. Before starting, let me say I'm facing a serious power interruption issue here. So if you feel any issue while I'm presenting, please let me know. Agri sir, please call me through WhatsApp or phone call, okay?
Okay, sir. Okay.
Okay, thank you. And first of all, thank you very much, dear coordinators, for inviting me for this session. It's my honor. And after a long time, I'm listening Dr. Jayaprakash sir presentation. He still have the track of ongoing research trends and all with his non-academic and admin duties. So I'm really happy to enjoy this section with you all. So let us make this more interactive. And my presentation basically included with general power system based and power electronic based research. I think the schedule was with the power converters. So, but I have already given many talks about the power converters for grid integration. So I would like to change the topic into EV charging stations and grid impact. This is the most recent and trending topic, I guess. And thank you, Dr. Sugesh sir, for asking a nice, intelligent question to Dr. Jayaprakash sir about the grid's reliability issue or stability issue while interconnecting new and renewable energy sources. So we will start from there. So here we are addressing the issue, stability issue and power quality issue of the grid or impacts on the grid with the EV revolution. So this presentation addresses the critical intersection of two major trends, the global surge in electric vehicles, that is EV, and capacity of our existing electrical infra. While EVs represent progress, their charging demands, especially fast charging, pose a serious threat to power quality. We will explore how integrating on-site solar generation and smart power electronic technologies like DStatCom can mitigate these risks. So finally, we will go for the remedy. So I'm starting my presentation here. I'm Dr. Nirmal Mukundan. I'm from Advanced Power and Energy Center, Khalifa University, Abu Dhabi. The electric revolution is here. We are witnessing a fundamental transformation, not a passing fad. Global EV sales, you can see the companies adopted EV technology, and some companies came with EV, started with EV, and the global EV market is now ruled by Tesla, BYD, Geely, and most of them are Chinese companies. They are fastly moving to EV. And Toyota is not interested in EV, they are moving to fuel cell. So the conclusion is we are moving from fossil fuel to EV. But there will be a question how this EV is charged, or how this EV is fueled. The representation of tectonic shift from internal combustion engines fundamentally altering global energy demand patterns. The electricity needed to power these vehicles will be immense, and the way we draw the power, often concentrated high power burst, is unlike anything the grid was designed to handle. That's the question asked by Dr. Sugesh sir. And but what fuels this revolution? That's the main concern when we are talking about EV. When we are seeing EV will be smooth, nice, and very attractive. But the problem with EV is how this EV is fueled. while EVs are celebrated for reducing tailpipe emissions, we must ask what is the source of electrons that charge them. If the grid is powered by fossil fuels, the environment benefit will be reduced. Instead of using fossil fuel based combustion engines, we are using EV, and the EV is charged from a long distance fossil fuel based power generation unit that there won't be any benefit. Instead, there will be uh, the problem will be drastic, and main challenge what we are facing in the present situation, especially in Indian scenario, is our aging grid. We can see our uh, distribution grid is like this. We can see these overhead lines are overloaded with service lines, mains, and sometimes we can see birds nest also with this. This is the EV diagram represented from modern countries, I mean developed countries. But when they are talking about these EVs, when they are talking about the distribution issues, they are also showing this diagram. It is from our Indian roads. And the modern reality of EV fast charging station is the opposite. They are highly concentrated, unpredictable, and massive point loads. Imagine the demand of a small factory appearing and disappearing at random locations. This EV tsunami threatens to overwhelm local distribution infra not built for such stress, because this is already our distribution system developed or designed for predictable, relatively stable demands. And this is the presentation roadmap of my presentation. To navigate this complex issue, we will follow a clear path. First, we will diagnose the problem into two parts: the EV tsunami and the grid. The part two, the hidden enemy is the power quality and power availability. These two, I know there are a lot of other small and bigger challenges, but these two are the major challenges with the EV integration with the grid: power quality and power availability. And we will find some solution, and we will talk about a solution which is DC.
Nirmal, I guess.
We are planning for integrated smart charging that will manage cost. From standard outlet 1 to 2 kilowatt manageable but slow. It has to be given for overnight charging. And in level 2, it's a medium level charging. It's common for homes, workplaces especially. It's for 5 or 6 hours for charging, and the slower one may be required for 10 to 12 hours of charging. And we have now modern DC fast charging, which is abbreviated as DCFC. This is 15 to 45 minutes required for charging a complete full car from almost 0 to 100%. And the battery is also developed for depth of discharge of 100%. The gas station versus the electron hub analogy, because we are planning, or we are proposing to replace the gas stations or petrol fuel stations with our EV charging stations. In Abu Dhabi and in UAE, most of these fuel filling stations are equipped with EV charging stations also. So we have to wait for 45 minutes, around 45 minutes to get fully charged. But we can refuel or fuel our combustion vehicles with 5 to 10 or 15 minutes. That's another concern. We have to develop a more and fast charging solutions. So Another main issue with the installation of this EV charging station directly to the grid is a hotspot problem, because um, this is a localized issue. Fast charging hubs are often built along highways or in commercial corridors or in homes. The clustering creates an extreme hotspot or demand on a specific part of distribution network. For example, if we have 5 or 6 transformers from a main transformer, distribution transformer connected, and one distribution transformer is given for EV charging station, that will get that may come under the burnout or blackout or brownout, depending on the charging levels we implemented. And these components, which might service a neighborhood, were never rated for such concentrated industrial scale loads, leading to rapid overheating and failure. Our power system is developed or designed in 20th century for constant demands. But so EV will impact this problem, impact the distribution grid. And we can see this is a 24-hour curve of impact of DC fast charging or DCFC. This is the normal curve. We can see the spikes in the load demand here. Irrespective of the ongoing demand or normal demand, these spikes are appearing in the load demand curve. But we cannot control this load demand, because these spikes in the load demands are because of the fast charge of DC fast charging of electric vehicles. We cannot control directly this fast charging because this is customer's need. Customer may need it at the night, at the midnight, or in the morning, or in the noon or something. So we don't have control in it. It is another main issue what we are facing in the starting of this EV system. And the EV charging challenges manifest as two interested crises. First one is power quality crisis, the fitness of electricity. Power quality is nothing but the fitness of electricity, how much pure the sinusoidal waveform is. We know there won't be 100% sinusoidal waveform if we are using power electronic equipments or static devices, but we are smoothening it to maximizing the quality of the sinusoidal waveform or the AC voltage waveform to reach the sinusoidal waveform. So, but we are facing transients, harmonics, reactive power, network unbalance, voltage variations, and flicker. These all are the main power quality issues what we are facing with the development of or with the involvement of power electronic devices. But luckily, the power electronic is the reason for these power quality issues, and power electronic is the solution for, remedy for reducing these power quality issues. And transients are very happening in a very small duration, and harmonics can happen for very long duration. And reactive power also is not a direct power quality issue, but this phase difference will cause a huge amount of current passing through our distribution network and causes heating. And network unbalance again causes circulating current in our machines, and voltage variations causes malfunction of our consumer equipments. And flicker directly affect our lighting loads and our sensitive electronic gadgets and equipments. And what is power quality? Actually, power quality is the health of electricity. How much pure is the sine wave? That measurement is our power quality. And how much the current is following our sinusoidal voltage. That is the measure of power quality. Think of the electrical grid as a water system. We are sometimes comparing it with a water analogy, and voltage is like water pressure. Frequency maybe 50 or 60 hertz is the steady rhythm of flow. Perfect power quality is clean water at perfectly constant pressure and flow. EV chargers distort this ideal. They draw current in jagged pulses, creating noise and pressure drops. Just as sensitive electrons can be damaged by poor quality power. So, can EV chargers themselves and neighboring equipments can get damaged with this EV integration? What is power availability? Is the power on? Can the grid physically deliver enough power? That is the main question. Because we demanding for around 500 kVA power, sorry, kilowatt power in very short duration. That is highly unacceptable when we are talking about a utility scale, because our power generation mainly based on turbines, heat turbines, fossil fuel based turbines, and even hydro. But these are not dynamic to generate this much power in a very short duration, and this power generation for very short duration needs optimization. We have to use other energy sources, really fast acting energy sources we have to use. Otherwise transformer will burn out, or blackout will happen. Transformer burnout is a irreversible process. We have to replace the transformer coils and transformers, and blackouts can be reversible with fast acting fuses or circuit breakers. And diagnosing the crisis, power quality is under attack. Now let's dissect the specific power quality ailments caused by EV chargers. Understanding this is the key prescribing the right cure. So first issue is the voltage sag. Voltage sag is nothing but a dip in voltage for a short duration. Number of cycles are dipped from our rated maximum voltage. Here you can see 100 volt is the rated volt. Our peak voltage is 325 volt. Here I have taken a percentage of the magnitude. So 100 percentage is the rated amplitude, and it dipped to a reduced level for few cycles, and it restored after few cycles to 100 percentage. This dip may be due to the DCFC, starting of DCFC, and our power system or our power generation stations require some few cycles to deliver this power. So sudden inrush current when DCFC station starts is the main reason when we are talking about the EV loads. And problem with this low voltage is the low power output. So how this voltage sag impacted our EV is slow charging and charger shutdown. Charger is sensitive to voltage fluctuations. So when the voltage dips, the charger gets shut down and stress on other equipments. Because here we may have EV and we may have also our computer or sensitive equipment. So all these equipments will get affected with this EV. So we are not saying EV is a danger. Is a danger to our power system, but we are seeing the opportunities as a power electronic engineer. These are our opportunities to research and develop our remedies. And in charging plaza, that's a charging station, multiple charger cycle on and off independently as vehicles finishing charging. This creates rapid, repetitive, small changes in total load. The result is a continuous, maddening, and fluctuating in voltage, visible as lights that dim and brighten rhythmically. Because the power curve never experienced such ripples or such spikes in the recent era. We are facing very rapid or very unrhythmic, we can say like unrhythmic flickers and fluctuations in power demand that causes voltage fluctuations and flicker. And another main concern is the harmonics. Harmonics are not transients. Harmonics are may be there for many cycles or minutes or hours. because our battery is DC. We need DC power. We are rectifying the AC power to DC, and we are using it. The diode bridge rectifier input current THD is around 44% if filters are not used. And if we are getting pure DC at the DC side, we have to bear a 44% THD in the input current of the rectifier. So that current will be flown through our distribution lines, and this distribution line will get a drop of this harmonic voltage. Harmonic current into impedance, grid impedance will give harmonic voltage drop, and our consumer equipments will get affected with this harmonic voltage drop. And harmonic distortion also heating the transformer core. You can see here, first one is a transformer core's diagram with the infrared picture of this transformer with without harmonics. That means fundamental voltage and fundamental current. Our load is non-electronic. Our load was a resistive load. We have connected resistive load, and our transformer core is like this. When we are increasing our harmonic with power electronic load, we get the coil is like this. Our coils are getting overheated, and these coils and this transformer is not designed for such purpose. Such sudden voltage and such sudden heating and overloading is not experienced so far, but due to EV integration this is experienced and it may get damaged. And another issue is low power factor. We have already seen this beer analogy. So power factor plays another role by keeping the true or real power constant, let's say K, and when the reactive power increases, this apparent power also will get increased, and the power transferred through our distribution system or distribution lines will get increased, and the heating loss and energy loss through the transmission lines and transformers will get increased. So this is also another issue, and especially when using inductive loads, the reactive power is the problem. And our EV loads and EV local loads also drawing reactive power. So cumulative effect is a transformer overloading and aging. Here we can see the transformer impact of harmonics, and it is overloaded like this. So its lifespan is reduced like this. So it's this graph is taken from I forgot to add the reference. I will share the slides and I will add the references in it. It's a case study, and they plotted this graph smoothly with lifespan reduction with harmonics in the transformer. And it's a news screenshot sharing here. How we connect theory to headline reality. We will see the EV can integrate into distribution network. We can get clean energy. Actually, that is not the case. This we are facing another issue. This news from CNBC why the electric vehicle boom could put a major strain on the U.S. power grid. It's a concern raised by the U.S. power grid because Tesla is booming everywhere in U.S. and people are moving from diesel petrol engines to EV due to high pickup and modern technology adaptation. Here, peak demand crisis network with EV, we can see here. This is the network demand, common network demand, and this is the common network demand, and this is the EV charging load. Here we can see the peak demand has reduced further. Actually, when we are developing or designing new technology with the existing power system, we are not burdening the existing power system. We are planning to, we have to reduce the burden of the power system. For example, when we designed or when we developed renewable energy sources, we try to reduce the peaks. So it's called peak shaving. We try to reduce the peak. But with EV as a load, the peak energy demand got increased. And also the infrastructures are a bottleneck. The weakest link is the problem with our transformer. So in India, they set the maximum solar installation 10 to 15 percentage of the rating of the distribution transformer. So our some of the larger consumers, they are ready to replace the transformer with their own risk. But this is a cumulative effect. Even if we replace the distribution transformer, our utility scale high power transformers, 11 kV or say 1144 kV transformers has to be replaced. That's a very slow and very astronomically expensive project. So that may slow down the EV generation, EV installation directly with the grid. So there was a case study. This narrative makes the problem real. A suburban neighborhood embraces EVs. A developer installs a fast charging hub anticipating demand. Within months, the local utility transformer begins failing repeatedly. Homeowners complain of lights flickering and electronics behaving oddly. An investigation reveals the root cause: the chargers are generating harmonic currents that overload the transformer and create voltage instability. This is a similar issue we faced in Calicut in a private hospital. They faced malfunction of their sensitive equipments, and they found one printer was functioning from the same line, and when the printer is working, the sensitive equipment got malfunctioning. I heard this case study from Pune during a conference. And here, the business impact is a downtime means lost revenue. We cannot wait till the power system get charged to accommodate all these EVs. So, but poor power quality means charger will get malfunctions, because chargers are very sensitive, especially for EV charging stations. They are sensing voltage, they are sensing current, they are evaluating the power, everything they are evaluating when connected to the grid. And when something went wrong or something goes below the permissible limit, that permissible limit or tolerance is very low. And if it goes below the limit, it will get disconnected. So charger malfunction and consumer dissatisfaction. Of course, the consumer will get dissatisfied, and utility penalty fees and lost revenue and failed business model. We may say the business model is failed. And utilities are in difficult position actually. They are often mandated by policy to support EV adoption and provide interconnection for charging stations, because we cannot say no to EV boom. In all over the world, especially in developed countries, they adopted EVs and they started localized energy generation for EV. But when we are talking about grid integration or grid connection, we have to rethink. We have to be planned. However, their primary duty is to ensure safe, reliable, and affordable power for all consumers or customers. They cannot allow a single charging hub to destabilize the voltage or burn out equipment for an entire neighborhood. This creates friction and can lead to lengthy, expensive interconnection studies and requirements, slowing down the overall EV rollout. And here clock is ticking. You can see the interpolation says at 2030 there will be 6.5 trillion US dollar investment in the total EV market. And you can see the Latin America, Asia Pacific won't be in a back. So we have to be ready with our system. So we have a lot of opportunities as power electronic researchers or electrical researchers, especially in power system researchers for forecasting these EVs. That will be very difficult, but forecasting this EV, power system researchers and optimization of energy sources will be opportunity for um, new PhD researchers and developers. So part two summary, the when more EVs are coming, fast charging demand will get raised. So power quality issues also will be there. So this is main concern. We have to keep it in mind. Grid stress and equipment aging will also be there, and reduced reliability and availability will be there, and this will slow down the EV adoption. But we have to increase the EV because all over the world EV is booming. So again, this will happen like a cycle. So we need a paradigm shift. That's here we are coming to solutions. Till now, till slide 27, we talked about the problems with EV adoption. Now we need a paradigm shift. Why we need EV? We cannot solve a 21st century problem with a 20th century thinking. Instead of just drawing more power from an already stressed grid, we need a new paradigm. Our response is built on three synergistic pillars. First one is to generate clean energy. Because this EV, for EV, we have to generate clean energy. That means the energy must be generated from non-fossil fuel based resources. But we know nothing is 100% clean. Even we are saying solar PV, solar photovoltaic technology is clean. The technology might be clean, but the solar panels generation cause a lot of carbon dioxide or carbon emission and utilization of our normal resources like silica and all. And again, this disposal of these PV panels after their lifespan is also another challenge and opportunity for market. So we have to generate clean energy, comparatively clean energy, and compensate and correct the power quality issue instantly at the time of happening. At the instant, we have to compensate and correct the power quality, and we have to manage and optimize our energy or power instantaneously and intelligently. So the remedy is an integrated solution toolkit. The solution is not a single silver bullet, but an integrated toolkit that combines mature and emerging technologies. This holistic approach addresses both the availability crisis and the power quality crisis. Here, first pillar is generate cleanly harness the sun. So cleanly harness the sun, I know we are comparing comparatively clean. We are comparing it with the fossil fuel based energy generation. Energy generation is clean with the PV, but for photovoltaic panel generation is not that clean. And for this is the first pillar. And we have to fuel the EV with our local, because generate power right where you consume them, reduce draw from the grid during the day. Because if we have EV here, this power generated from miles away, kilometers away, power generation, PG, let it be. So if we have a localized energy source, let it say ES, if we are able to compensate, or we can fuel this EV from this energy source, we can reduce or we can remove this long transmission line or distribution support and we can make it as an island. So this is a localized energy generation. And peak shaving and load shifting. This is a killer app for solar and batteries. A battery energy storage system comes into picture at this stage because we cannot rely on solar energy, because we cannot rely on EV customers or EV consumers, because they can charge their battery at any time. So there will be high reliability issues with EV. If we are trying to solve the reliability issue of the EV or power issue, availability issue of the EV with solar, that will worsen the case, because PV also doesn't have reliability. So we have to use an energy storage. Currently, the best energy source storage system we are using is battery energy storage system. I'm not underestimating the fuel cell and hydrogen energy, other energy forms, but battery energy storage systems are the um, one of the most acceptable and very easy to install. And we can see the battery storage, battery technology is developing day by day, very fast. And when I'm talking about the battery, recently we got from in Khalifa University Advanced Power and Energy Center received a query from Yas Energy. It's from Dubai, Abu Dhabi. They developed a battery with the sodium ions, and they called us for testing this battery. They got a purchase order from Neom Project Saudi Arabia, and they need to test the battery for long term and transient conditions. So today or tomorrow, the battery pack will arrive. It reached Abu Dhabi port and waiting for clearance. And I have to go back and conduct the test for Yas Energy. So here, BESS or battery energy storage system can be charged by solar or by cheap off-peak grid power. You know, the grid power price is fluctuating with the demand. And during the expensive evening peak, the BESS discharges to the power chargers and shaving the peak demand seen by the grid. This saves enormous cost and relieves the grid stress. Here, this is another advantage that I just said. It's a energy island. Solar can create resilient energy islands for critical charging. Also, this is also can be reverse used for V2G. It's nothing but a vehicle to grid. And here, this is explaining to the G2V. That's a grid. Sorry, grid to vehicle. Here we can see all grid is shut down, and this house is only got power from battery packs, and this EV is getting charged from this EV charging stations by using the stored energy even at the night. So it can be used like a island. So this is another charged by the sun is another slogan. It's a powerful brand differentiator that authentically aligns with environmental missions of EV drivers. We have already published papers with EV parking lot or PV parking lot. This parking lot is with roof with the solar PV, photovoltaic panels, and we have charging station underneath. And we should have energy storage to maximize the energy generation or maximize the energy transfer from the photovoltaic panels. This is what we discussed just now. The main limitation with the solar is its intermittency, its dependency on the climatic conditions. The generation drops to zero at night and on cloudy days, precisely when charging demand may remain high. Because cloudy days doesn't make any difference when talking about the EV. and other consumers. So the demand might be high, but our generation will be low. Furthermore, solar inverters alone do not solve power quality issues like harmonics and flicker. We have to use power electronic components. They are part of the solution, but not the old solution. We have to think about power quality support for photovoltaic technology. Here we can see some of the graphs. So it's a billion light duty EVs, global electric vehicle growth around 2035. They are interpolated to this level, and solar rate of solar photovoltaic technology or solar power generation is reducing like this. And the pillar 2 is the main thing. That means pillar 1 was solar, clean energy, and pillar 2 is how to use this energy efficiently or effectively. The solution is DSTATCOM. This is a DSTATCOM installed in a power station. And what is DSTATCOM? DSTATCOM actually is a distribution static compensator. It's like a shock absorber. The dedicated power quality specialist is a power electronic device that acts both as a shock absorber and a filter. Its key attribute is speed. It reacts in milliseconds. I will show you how fastly our our proposed system worked in our laboratory equipment that I have added at the last. Here, DSTATCOM's core function is voltage stabilization. This is the main function, and we used when we are talking about the EV. And it continuously monitors voltage. If it detects a sag, it injects reactive power to boost it. If it detects a swell, it absorbs reactive power to reduce it. It holds voltage rock steady because it acts in milliseconds. We know a 50 hertz is 20 milliseconds, is one cycle. Within that cycle, it will act. Maybe in 1 or 2 cycles, the DSTATCOM will act and make our voltage rock steady. So its another core function is harmonic filtering. So it acts as an active filter. It measures the distorted current from the charges, output current or load current it is measuring. And if it is not sinusoidal waveform, the sinusoidal it has to make the grid current sinusoidal. So the remaining waveforms, the harmonics, is supplied from our DSTATCOM or our inverter. So finally, we are making the grid current as sinusoidal and reducing the harmonics and reducing all issues with the harmonics and overheating, burnout of transformers and all. And the power factor correction is another main advantage. With may our customer equipments needs reactive power. This reactive power is directly taken or drawn from the grid because it is directly coupled with the PCC or point of common coupling. But if we are connected our distribution static compensator like a shunt, we are delivering. This is our grid, and this is our load. Let it be EV or any other loads. We are connecting our static compensator here. And when the load demanding harmonics, let it be H, this H is supplied from here. And when it is demanding reactive power Q, this Q is supported here. So here we will see only P. P is nothing but active power. Here, the STATCOM versus traditional capacitor banks. Old school capacitor banks are slow. We know we started reactive power compensation with our capacitor banks, but our old school capacitor banks are slow. And the main problem with the capacitor banks are its fixed rating. When the load is fluctuating or load is reduced or load is increased, the capacitor bank rating won't be changed. The capacitor will be at a fixed rating. Either it will be over compensating or under compensating. So D-Statcom is fast, precise, and immune to resonances. And capacitor also causes resonances. When we are installing inductive equipments or motors, we have to evaluate the total capacitance of the point of common coupling to avoid resonance and high inrush currents. For dynamic EV loads, it is the superior modern choice. That is nothing but D-Statcom. Here I showed you how our system is connected. This is grid. This is our EV. If our EV requires a current which is like this instead of sinusoidal, if it is demanding a triangular waveform, this will be taken or drawn from the grid. But we have connected a D-Statcom here, and we have given waveform to make this grid waveform as sinusoidal. Here you can see this is the load current. Let represent it like IL, and this is the current supplied by the D-Statcom. When we are seeing this current, we won't feel pleasant because this is an annoying one. But when we are seeing the result here, we can see we have reduced the ripples. We have reduced the ripples to like this, and we generated almost sinusoidal waveform, and we achieved THD around 4.46%. This is IEEE well fit in IEEE 519 standard. And next is our pillar 3. Pillar 3 is smart charging and energy management. We need smart charging. We cannot avoid smart charging or fast charging. So what we need is a smart charging. We have to manage our energy to get this smart charging. So we have to communicate with the grid to know real time electricity prices and grid stress level, because what is the price level in the present condition that we need to know. So we need a proper communication with the grid about the prices, and we need to know what is the grid demand, whether the grid is requiring power or grid have surplus power. Communicates with every charger and controls their power draw. We have to communicate with the charging stations, and we have to know. But the problem is we cannot forecast the charging pattern, because this is open to customers or consumers. Consumers can go to any charging stations at any time. They are free to go. They are free to charge. So we cannot. It is I can't say as an engineer or researcher, I cannot say we cannot forecast, but it is very difficult to forecast. It's a challenging job to forecast the charging. So we have to communicate with every charging stations or chargers to control their power draw, and manages the power solar PV system and battery storage. We have to monitor it, and load balancing, dynamic rates, and incentives we have to evaluate, and we have to make a decision instantaneously. In split second, we have to make a decision for this energy management. So this is another challenge that we are facing. So it's another opportunity for researchers to connect our brain with the EV technology. So we need energy management system and intelligent smart charging. And smart charging, load balancing, and dynamic rates. This I already discussed just now. And this is the ultimate trio: solar, storage, and D-Statcom. Actually, this is taken not from my paper. I have cited this paper here. Here they have used a separate DC-DC converter. Here we can use it with the boost converter also. For simplicity, I'm saying it's a boost converter. So we have a boost converter to get a maximum power generation, and we have battery energy storage to support the PV system, and we have a control. This is their proposed control. We need intelligent control to controlling these power electronic switches. This is a three-phase, three-leg inverter interfaced with the grid through interfacing inductor. These inductors are called interfacing inductors or integrating inductors. And this is our distribution system. Here, our nonlinear load is nothing but EV in modern power system. So solar PV to DC power, battery storage as a buffer for PV to increase the reliability of the PV, and DStatCom, this control operates or defines the STATCOM operation of this inverter. So it enhances our grid power quality, and all tied together by energy management system, nothing but EMS. Grid connection is stable and optimized. Here we have energy here and we have power quality here. So we can control the current as a constant, IG as a constant. If the load is reducing, we can charge the battery, or if the load is increasing, we can discharge this battery. Like that, we will get a constant power and good power quality. So this is the ultimate trio: solar, storage, DC system. Sorry, DStatCom. So the question is how they work. So in a sunny day scenario, we have a battery system. This is self-explanatory actually. Solar produces more power than the charges needed in the sunny days. We have to design solar like that, because solar power availability for a day is 5 to 6 hours. So we have to charge our battery for full night from this solar PV panel. So we have to produce more power than the load requirement during daytime. So the excess power is used for charging the battery. The DStatCom ensures any solar power exported to the grid is perfectly clean. The EMS or energy management system maximizes self-consumption of solar or maximum power extraction. So in the cloudy evening or in the peak scenario, the grid is stressed and the power is expensive. The EMS dispatches power from the batteries to supply the chargers, performing peak shaving as large loads switch. The DStatCom instantly corrects any voltage fluctuations. And how they work together, yeah. So it's a case study, electron hub or charging plaza or charging station. So proof of concept is a real charging plaza with the 10 DCFs. DC fast charging was suffering from the exact problem described: voltage complaints and transformer overheating. The integrated solution was deployed: a 500 kilowatt solar canopy, a 1 megawatt hour battery, because battery has to support the overall system, grid, as well as the EV charging station for more time, around 18 hours, 18 hours in a day, and 500 kVAr DStatCom for power quality. That's sorry. The results were transformative: 40% reduction in grid energy purchase, elimination of all power quality complaints, removal of utility penalty fees, and the ability to market to site 100% of the cell and green hub. So attracting more consumers, it can attract more consumers if we are installing PV, battery, and DStatCom as a overall system. And financial justification for using DStatCom and battery. Solar DStatCom EMS are capital investment. Yes, capex. It is called capex, and they slash operational cost. Or it is nothing but it is called opex. So it will result low energy bills. So why solar self-consumption and peak shaving? So it can give the surplus power generated during daytime, or if it is in the peak time, to the grid. And upgraded costs can be compared, and they can manage the power flow based on this cost, and higher revenue can be generated, and green premium resilience, and we may get subsidies from governments. So OPEX will be very low, but CAPEX will be there. When we are installing a fossil fuel based energy generation system, the CAPEX and OPEX will be there. So we can justify like this. I haven't gone through a proper research of this financial justification study, and I read some papers, and they are claiming that this Statcom solar EMS are the promising one compared to other technologies, because we cannot say no to EV booming or EV revolution. And the business case is clear. Investing in power quality and on-site generation isn't an expense. It's a foundation for scalable, profitable, and future-proof charging business. Yeah, of course, we can scale the generation system and EV charging stations. Once we start with one charging plug, we can scale to large number of levels, and also we can install more number of PV panels. Towards a smarter ecosystem, the integrated toolkit is the foundation. Now let's look at the future. It enables where charging infrastructure become an active, beneficial participant in smarter energy ecosystem. So another idea is vehicle to grid. So it's a next frontier. EVs are essentially batteries on wheels. So it's like a moving energy storage. So why we can't use that energy storage when it is not using? I mean, when the vehicle is parked with a fully charged condition, and the customer needs only 20% of the total charge of the battery to reach his office, then remaining 80%, at least 60 to 70% of the charge we can use to power our house during peak power demand time. That will only happen because we cannot charge our home during low peak demand or low demand time, because during high peak demand time energy cost will be high. That time we can consume the energy stored in our cars. So EVs are essentially batteries on wheels. That's what I said. V2G technology, that vehicle to grid technology, allows them to discharge power back to grid and build during times of peak. Just a second. Yeah. Hello. Can you see my slide 52? Akhil sir.
So now it's vehicle to grid, that slide.
Yeah,
Vehicle to
52,
grid
right?
EVs.
Yeah, thank you very much. Thank you very much. So vehicle, I already discussed with you when I showed an image. We can use the vehicle as a energy storage to power our grid or power our home. So vehicle to home, home to vehicle. This is another research area for research opportunity for researchers. And this is our smart grid or smart system. The future grid will be a network of intelligent nodes, EV charging stations equipped with solar, storage, and power quality controls will become active grid participants. They can provide essential grid services like frequency regulation, voltage support, and black stat capability. Because black stat capability is nothing but islanding technology or anti-islanding technology. Because when the power is out, the grid power is out, we can use the EV stored or the stored energy in our home with the BESS. We can use those. and they can provide essential grid services like frequency regulation that by exchanging active power, voltage support by exchanging reactive power, and blackstacking, forming the building blocks of community microgrids that enhance local resilience and efficiency. So we have this smart grid technology. Along with this smart grid technology, there is another main research area developed is AI, artificial intelligence. We know we cannot predict or we cannot optimize all this instantly, because these EV power demand variations, PV power production demand variation, grid power rate variations are instantaneous. We cannot predict them, or it is very difficult to predict them. So we need someone to focus or someone to monitor all these variations closely. So we need AI technology. Like a human brain, it will act like a human brain. We can train this AI and AI models and make them capable to make decision based on our demands. So standardization, and when we are talking about the standardization and regulation, um, one of the major regulation is 1547. This is for interconnection of distributed energy storage system, and grid code will evolve to require the regulate grid code will evolve to require charging stations to maintain power quality. So modern grid codes like 1547 2018 are expanding their scope to strictly limit the harmonic injection, voltage fluctuations, and other disturbances that distributed resources like EV hubs can cause. The table shows this evolution proactively installing solutions like DStatCom ensures the power quality of the grid. So we cannot install diode bridge rectifier or rectifier based charging station directly with the grid. We have to use DStatCom like active power filters along with these charging stations. And this is the list of international standard assisted in Indian standards. Oh, I'm sorry, unfortunately, these tables are not clear. Here I have given the citation, and I'm sure that you can find these standards, Indian standards here. Most of them are European and American standards, and yeah, these standards will give maximum voltage fluctuation, maximum current ripple, maximum voltage ripple, maximum frequency variations like that, and also maximum harmonics injection with the grid. So these are the comparison between Danish and Indonesian GCs. So grid codes. So these grid codes are just for reference. Uh, this is the technical requirement uses for connected to network, that is 49 to 51 hertz has to be maintained for every consumers when interconnecting our EV or distribution system, and plus or minus 5% and 10% must be the voltage rating, and installed the capacity must be in a 10 to 15%, and we cannot imbalance or we cannot unbalance our load more than 1%, and the power factor must be 0.9 lagging or nearly we should have a nearly unity power factor. So the problem is we have stringent rules for connecting distributed resources and EV charging stations with the grid. We have to obey these grid rules. So what is the solution? Solution is the trio: solar, battery, and DStatCo. Here I have developed control for grid connected PV system addressing nonlinear industrial loads. This is EV. Sorry, this is EV. And I'm not focusing on the EV power and EV currents. My focus is on the grid currents. So, but I'm not connecting a battery here. I'm considering this grid as a main utility grid, or it is connected to main utility grid or infinite voltage bus. So I have a solar photovoltaic panels. This is a published work, and now this work doesn't have significance because these works are not encouraging nowadays by the journals, because it doesn't have an energy storage system. It makes intermittent power flow to the grid, because this is also, this nonlinear load or EV load is intermittent. We cannot predict, and this solar PV array generation also is unreliable due to the climate dependency. So it's a published work, and I will show you how to deal with this grid connected PV system. Here we have a solar PV panels. We have connected a boost converter here. This is a boost converter. We have a three-phase, three-leg inverter, and I have connected it with the PCC. This is nothing but point of common coupling. I am measuring grid voltage is Vs, and grid current Is, and load current IL, and PV array voltage IVB and IPV are measured. This is VB is not PV array voltage. I'm sorry, PV array voltage is VPV, but I'm measuring the DC link voltage VB. Because of this boost converter, I know the duty ratio, so I'm deriving the PV array voltage from this VB or DC link voltage from the boost equation. We know the VB equal to 1 by 1 minus D into VPV in a boost case. So this is the proposed control approach. So here, in one side, I am expecting voltage harmonics or voltage fluctuations. Even if I say this is an infinite voltage bus, I should be ready with the withstanding all voltage fluctuations. So I have, for a safety purpose, I have measured or sensed three-phase grid voltages Vs, A, B, C, and I have DC link voltage VB. I have load current ILA, like that. And these all are the voltage processing loop. This is the current processing loop. This is the MPPT block or maximum power point tracking. And sorry, this is the MPPT block. This is for active power component generation. And I'm from VSABC. I'm finally generating USA, USB, and USC. These are unit voltage templates for grid current references. This grid current, what I'm expecting is a pure sine wave. So this pure sine wave must have a shape and magnitude. So this USA, USB, USC are three equally facially displaced voltage with the unit amplitude. So this will give the shape. So amplitude will given by this ILP. ILP is derived from the load current. This is a laboratory setup. Before that, I will show how the control block diagrams, our control systems border diagram we have drawn, and we found it works like a band pass filter, and also it gives a fluctuating band pass with respect to the gain factor K in the control loop. So we can increase or decrease the band gap based on the application. If we increase, the system speed will increase, but the filtering quality will reduce. If we reduce or narrow down the band pass, our filtering quality will improve, but our system will get delayed or reduced speed. We may have to wait for few cycles. And we also checked the pole zero port, and we found all poles and zeros lies on the left hand side of the j omega axis of the S plane. So we found that this control system is stable. We also did the overall control stability analysis with this control and with this power electronic equipment and all. And the detailed analysis uh, will be when I present it will be boring. So I can give you the reference or citation of the paper, so you can check the theory and mathematics in it. And if you have any doubt, you can contact me. I will share the basic files. In our Khalifa University laboratory, we have this setup. We have power quality analyzer equipments, and we have programmable grid. This is Synergia G15 is the model. We can program this grid. I used my laptop to program the grid. We can inject from here. We can inject harmonics, order harmonics, phase harmonics, amplitude, and we can see a preview here. We will get the similar waveform from the Synergia. And this is the real-time waveform we observed from the Synergia through this MATLAB, Semicron, this DSpace MicroLab box. Actually, really sorry for this. We have this DSOs here, and we have PV emulator, nonlinear load as a direct rectifier, three-phase direct rectifier I used with the capacitor and resistive loads as a EV load or nonlinear load. And the Semicron IGBT module we used as a three-phase inverter, three-leg inverter. And this is a Opalati OP5000 is the voltage and current sensor. This is a PCC. This is the PCC actually. Here I shown in the inside. And I have also installed the breakers. This breakers is for safety as well as making disturbances in the load side. So I wanted to check how my proposed system works or behaves with respect to the situations. This is first result we observed with the real-time performance of the proposed control. We check the variations of the internal controls signals with the input. And here, this is A. This is A, and we can see voltage waveforms here, VSA, VSB, VSC, and here at this point, the voltage will become distorted. Immediately will get distorted, and this is the total waveform. This is the total waveform, and this is the total current, total unit voltage templates. I told you this is our final output from the voltage processing loop, USA, USB, USC. So with the distortion, this is the unit voltage templates, three-phase symmetric balanced voltage unit voltage templates we got here, and we can see with this voltage distortions unbalanced or with the harmonics, this is not get affected. These three waveforms are not get affected. These are balanced and steady always. And in the B diagram or B result, it's a real-time result. It's taken from this Yokohama DSO, digital storage oscilloscope, and with these results we are checking balanced load, unbalanced load, and again back to balancing loads. I'm sorry, this is C. So this load balancing and unbalancing. Here, this portion is zoomed and shown here. You can see when the load is disconnected in one phase load is disconnected, and the grid current is not affected. The grid current is sinusoidal, very near to pure sinusoidal waveform. And here, the grid load current is restored. And when the load current is restored here, this is the zoom view. The grid current is not affected. This is sinusoidal and 180-degree out of phase with the phase voltage, because we are injecting grid to the grid. And here in the B diagram, we are checking the grid side harmonics and unbalancing DC offset in the grid voltages, and also restoring the grid into balanced and harmonious grid. Here we are making the DC offset, and you can see this blue color waveform is get a DC offset, and it is getting increased compared to other voltage levels. And but our USA, that means the unit voltage template, is sinusoidal, and these are the other internal control signals, V alpha, V beta, and all. And here we will see restoration. That means the DC offset is slightly reducing, and it is settling to 0 DC offset. Here also, if we are checking here, this is a pure sinusoidal waveform. It does not have any fluctuations or spikes or oscillations. And here we are checking normal grid with the voltage sag, and normal grid is going to voltage sag and again restoring to normal grid. Here you can see the grid voltage amplitude is reduced, and our grid current along with the grid voltage are given here. It doesn't have any amplitude change, it is constant. And here voltage swell, that means voltage amplitude is increased, and the voltage swell is shown here. Here you can see the voltage swell, and here it is restored to normal level. Again, our grid currents are sinusoidal and 180-degree. Here our 180-degree out of phase with the grid voltage because of the power injection towards the grid. Here grid voltage are unbalanced. Here you can see unbalanced grid voltage is occurred, and here unbalanced grid voltage are occurred. So zoomed view, dynamics 1 I marked as dynamic 1, dynamic 2. Zoomed view shows sinusoidal voltage and sinusoidal currents. Sinusoidal voltage is not our concern. Sinusoidal current, that means grid current quality, is our concern. For achieving that, we are how we are achieving it is because we are injecting non-sinusoidal waveform. This non-sinusoidal waveform contains harmonics for the load as well as active power for the grid. And here we will see grid side and load side, load side demand variations, high frequency, normal frequency, and normal frequency. Here normal frequency to high frequency shift is occurred in the grid side, and how our system is withstanding the grid frequency variations, that is achieved here. We are not observing or witnessing any peaks or overshoots in this grid current waveforms, and harmonics in grid voltage that we already seen. And here this is the and this is the power quality analysis we did with the grid control system. Here this is the grid voltage, and this is the load current, and this is the grid current. These diagrams and these waveforms are self-explanatory. By observing these grid voltages, you can see there are some harmonics in it, And when we checked with the power quality analyzer, we received 5.1% THD, smart DA. And when we did the analysis of this load current, this is almost square or pseudo square sine wave with one side offset. And here we received 27%, 6% THD with the load current when power quality is checked. But when we check the grid current harmonics with the effect of our distribution STATCOM operation of our grid connected PV system, we achieved 2.8% THD with the power quality analyzer result. So here we are analyzing or comparing our results with DSTATCOM, active filters, passive filters, and we will get less than 2 millisecond reaction time with our proposed system. And THD reduction is less than 3%. And DC offset is fully removed. And extra hardware cost is not required, but we have to limit the total reactive power compensation and harmonic power compensation within the rating of the inverter. And we have obeyed IEEE 519 standard. That means the grid current THD is maintained within the 5% limit. And PV integration is native with this technology. And scalability is high. We can scale this system to any power level by replacing the inverter and components. So the path to sustainable EV integration. Let's recap. The challenge is clear. The unmanaged EV charging degrades power quality and threatens grid availability, creating a vicious cycle. The solution is an integrated three-pillar approach. That means solar, storage, and DSTATCOM for instant power quality correction and smart EMS for intelligent optimization. This is the proven path forward. And the call action is charging operators and developers future-proof your investments. Choose integrated solutions that guarantee reliability, low operating cost, and compliance. Don't just build a charger. Build a smart energy asset. That is the call to action for developers and operators. And for utilities, move from a reactive to collaborative model, develop innovative tariff structures we need, demand charge management, grid services payments that incentivize developers to invest in grid-friendly infrastructure. And policymakers and regulators accelerate the transitions, update grid interconnection codes and builds regulations to encourage or mandate power quality mitigation and on-site generation for medium and large charging hubs. Support pilot projects and funding for smart charging infra for the development of and maximum utilization and efficient utilization of EV, ongoing EV revolution. So this is a collective goal, a future where the EV revolution is powered not by a strained, dirty grid, but by a symbiotic relationship between vehicles, renewable energy, and intelligent infra. We can achieve seamless charging for consumers, clean energy from the sun, and reliable power for all. We can power the revolution without breaking the grid. That is the final statement of this presentation. And thank you all. Thank you very much. And I hope you were there with me during this 1.5 hours. And sorry, more than 1 hour. I took 1 hour. And some of the slides might be boring for power system engineers and some might be boring for power electronics engineers, but these power electronics, power system, and these engineering branches has to be unite for for powering the revolution without breaking the grid. Thank you for all. And if you have any questions, please, we will discuss here. And I don't actually encourage questions. I encourage discussions because I am also a learning researcher. I like to learn from you. If you have any thoughts, you can share here. I agree with your thoughts, and I will also look into your thoughts, and we will do more research into it. And if you have any future ideas or future thoughts, you can write to me or you can text me directly. This is my email ID and business WhatsApp. Thank you all.
Thank you, sir.
Participants, we can have a discussion here. So you can share your thoughts on the session. We can have a discussion.
Or I will share the slides. If they have any ideas to discuss, let them contact me directly.
So then I think we can conclude our today's session. So thank you, Dr. Nirmal Mukundan, for your valuable session. I think all of the participants will get some insight into the topics. So thank you very much for joining us. Thank you, sir.
Thank you very much, and thank you everyone for joining us. For this is first time I'm seeing this many participants for FDP, and thank you all for your positive comments. And if you have any negative comments, feel free to text me in a personal message. Okay,